Got an exam question walkthrough here for Year 13 equilibrium. So the question looks at the equilibrium constant Kc, calculation involving Kc, the equilibrium constant Kp, and explaining a shift in equilibrium in terms of Kp. Don't forget to like and subscribe, and if you wanted to leave a comment in the comment section, maybe suggest a future topic, that would be brilliant. Okay, so here's the question. It's on 2 slides, so as always, I'll just click through the 2 slides. You pause the video, have a go at the question, and then play on for the answer. Okay, so part A, we've got to write an expression for Kc for the equilibrium and state the units. So for this expression, we've got NO2 in square brackets squared on the top divided by NO in square brackets squared multiplied by O2 in square brackets. So now for the units, just show you where they come from. So basically all of these square bracket terms represent moles per decimeter cubed. So essentially we've got moles per decimeter cubed squared on the top divided by moles per decimeter cubed squared times moles per decimeter cubed. So obviously we can cancel those terms out. So we're left with 1 over moles per decimeter cubed, which when you take everything up to the top, you flip the sign of the power, and so it becomes dm to the 3 mol to the minus 1. If you've written mol to the minus 1 dm to the 3, that's fine as well, but conventionally positive powers are written first. So moving on to part B, we need to calculate the amount in moles of NO2 in the equilibrium mixture. So essentially we need to find the NO2 concentration from the Kc expression and then turn that into moles using moles is concentration times volume. We've got the volume of the container there at 4 dm cubed. So the first thing I'm going to do before I put anything into the Kc expression is turn these moles into concentrations. So that's moles divided by volume is concentration. So we get 0.1 for the NO and 0.2 for the O2. So now I'm going to rearrange this Kc expression. Remember, we want to calculate the concentration of NO2. So the first rearrangement will give that. So NO2 concentration squared equals that. And we'll put a square root sign in, so we get that. So now we know everything that needs to go in there. We just need to put the numbers in. So NO2 concentration is equal to the square root of those numbers there. Remembering we need to square this one. So that comes out at 0.3. Remember, this is a concentration, so it's moles per decimeter cubed. And then the moles is concentration times volume, 1.2 moles. So moving on to part C now. So it's the same equilibrium, but we're now dealing with Kp. We've got to use these Kp values at the 2 different temperatures to decide whether the forward reaction is exothermic or endothermic. So if you see what's happening, the temperature's going up, Kp is going down. So basically, temperature increase is causing this equilibrium to go to the left or to go in reverse. So that reverse reaction, that backwards reaction, must be endothermic. Remember, temperature increase always favours the endothermic direction, and so therefore the forward reaction must be exothermic. So how we're going to write that? Temperature increase has made Kp smaller, so the reverse reaction is endothermic, therefore the forward reaction is exothermic. So final part of the question, we've got to state and explain in terms of Kp, so we can't use Le Chatelier's principle, how we'd expect the equilibrium position to change with an increase in pressure but temperature kept the same. So if we put a Kp expression up for the equilibrium, you can see that if you increase the pressure of the system, all of the partial pressures are going to increase. But because essentially you've got squared, the increase is squared on the top, but cubed on the bottom, the denominator term is going to be affected more. So this is going to increase more than this is going to increase. And the knock-on effect of that is it's going to decrease Kp. Temperature is the same, so Kp has to stay the same. So the numerator term has to increase, or you could say the partial pressure of NO2 has to increase to restore Kp. So how's the equilibrium going to do that? It's going to move to the right.